This section is the modern view of electronic structure, wave or quantum mechanics. So, goals. Understand that the position of an electron in an atom is not known with certainty. Only the probability of the electron being at a given point of space can be calculated. This is a consequence of the Heisenberg uncertainty principle. And understand that the modern view of atoms describes electrons as waves and identifies orbitals as allowed quantized energies. Describe the allowed energy states of the orbitals in an atom using the three quantum numbers n, l, and m sub l. Okay, so when we look at quantum mechanics, also called wave mechanics, this is a model of a hydrogen atom developed by a guy named Schrodinger. So there are some problems with Bohr's model of the atom. One of the problems with Bohr's model of the atom is, why do we have quantized energy levels? Why is there n equal 1, 2, 3, and so forth? He just kind of put that in there because it worked. And since the electrons are negative and the protons are positive, the electron, which is orbiting the nucleus, should spiral into the nucleus. Thirdly, if the orbits are like planets, so if you think about Earth, Mars, Venus, and our solar system, it's a disk. It's not a three-dimensional thing. So if all of these orbits for the electrons are like the planets, you would have a flat atom. So what was Schrodinger's solution? Schrodinger's solution was, well, you know what? If particles can have wave-like properties, then so can electrons. Electrons are a particle. And he was going to treat electrons as a standing wave. So with a standing wave, it's like a guitar string where you have these certain wavelengths between the ends of the places where the string are attached. So with standing waves, you can only have certain waves that'll work between the ends here. So it's like a guitar string. Well, he wanted to represent these standing waves as these math equations called wave functions. And this is called psi when we say that in English. Okay, so with the quantum mechanics, here are the pros of your standing wave model. Here's your proton, and you treat the electron with a standing wave. So this is a standing wave kind of put as a circle around the proton. Here's another standing wave. And this standing wave, this one doesn't work because the wavelength isn't the right wavelength, as it were. So this is not a possible solution for an electron around the proton. So only discrete standing waves are possible. Psi gives the energy of an electron for a given n. Psi squared gives the probability density, the location of an electron for a given n. The other thing I should say about the standing wave model is psi has three variables. N, L, and M sub L. And we'll see more about that in just a moment. So, characteristics of your psi or wave function. The three variables, the principal quantum number is n. And these are some rules that you want to understand and be able to use. The principal quantum number describes what's called the shell in this model. And the allowed values for n, the rules for n, are that n can equal 1, or it can be 2, or it can be 3, and so forth. And they're analogous to the levels in Bohr's atoms of n equal 1, n equal 2, n equal 3, and so forth. So this principal quantum number actually relates to Bohr's levels. And so that's why a lot of times when we look at Bohr's model, we call those n's principal quantum numbers. Now, L refers to something called a subshell. It turns out that every shell, which is a spherical type region of space, each of those can be subdivided into subshells. So if you had an apartment building, each apartment would be a part of the building. Subshells are part of the shell. Now, this variable is called the orbital angular momentum quantum number. And I've heard a lot of people just call it the angular momentum quantum number. So the rules for this, when we assign numerical values to them, are as follows. For a particular n, L can be 0, 1, all the way up to n minus 1. We'll look at these rules and how they apply in a little bit. M sub L is called the magnetic quantum number. And for a particular L, M can be 0, plus or minus 1, plus or minus 2, all the way up to plus or minus L. And so for a particular N, you can have particular L, and for a particular L, you can have particular M sub L. And we'll see how all of that plays out in a little bit. Right now, this is supposed to be a little flaky for you, but we'll see hopefully in a moment how it plays out. So if given values for N, L, and M sub L, this describes a region of space where the electron is likely to be found, a region called the orbital, and it gives the energy of the electron. So let's take a look at, let's see. I have a question here. I don't think, oh yeah, I think we're ready for that. Let me take a look at some of these other questions here really quick. Okay, we're ready for these. So based just on these rules, let's take a look at what the answers are or how we figure it out. So I'm going to write down the rules again for the different quantum numbers. So N is equal to 1, 2, 3. L is equal to 0, 1, all the way up to N minus 1. And M sub L is equal to 0, plus or minus 1, all the way up to plus or minus L. So these are the rules that we need to follow when we're trying to figure out these following questions. So when n equals 4, what are the possible values of L? So for n equals 4, we have L can be 0, it can be 1, it can be 2, and it can be 3. But it can't be 4 because L can only go up to n minus 1. 4 minus 1 is 3, so those are the possible values. So you can have a 4, 0, you can have a 4, 1, you can have a 4, 2, and you can have a 4, 3, where this is the shell and this is the subshell. Now, one of the things I didn't tell you about the subshell is that the subshells also have letter designations for these numbers. So the letter designations would be as follows. You could have a 4S, a 4P, a 4D, and a 4F. So these are subshells, and they're in the fourth shell. So you have to remember this order, SPDF. Some people do fine trying to figure out the order, some people don't. Some people do fine. So that's how I remember the order. Okay, so for this very first question, what are the possible values for L? 0, 1, 2, and 3 because of this rule where L goes all the way up to n minus 1. When L is 2, what are the possible values for M sub L? So if L is equal to 2, M sub L can be equal to 0, plus or minus 1, and plus or minus 2. So that means we can have the following values. If L is equal to 2, M sub L can be negative 2. If L is equal to 2, M sub L can be negative 1. If L is equal to 2, M sub L can be 0. If L is equal to 2, M sub L can be plus 1, and it could also be plus 2. So there are 5 different sets of numbers that will work for L equal 2. Now, it turns out that each one of these refers to something called an orbital. And that's a region of space where you're likely to find an electron compared to where the nucleus is. All right, so that's the first and the second question. Now, for a 4s orbital, what are the possible values of n, L, and m sub L? So we need to remember this, that for the different values of L, of 0, 1, 2, and 3, the letter designation is SPDF. So for this particular problem, when they say 4s, that means n is equal to 4 and L is equal to 0. Okay, so I'm going to put a little line through there. So if we know that L is equal to 0, that means M sub L is equal to 0 plus or minus 1 plus or minus 2 all the way up to plus or minus L. So in this case, M sub L could be 0 all the way up to plus or minus 0, which means it can't be plus or minus 1 plus or minus 2. So M sub L is 0. So that means that if n is equal to 4, if L is equal to 0, M sub L has to be 0. So that means we have a 4, 0, 0. And this is a particular orbital. Okay, so there's only one answer here. Now, for a 4f orbital, what are the possible values of n, L, and m sub L? So this one is actually quite a long answer if we want to look at it. So let's look at it. So for a 4f, and looking here at, I'm going to draw this over here. If L is 0, 1, 2, 3, the letter designation is SPDF. So when we have a 4F, we have N is equal to 4, L is equal to 3. And what are the possible M sub L's for this? Well, you could have M sub L equal to 0, plus or minus 1, plus or minus 2, and plus or minus 3. So when we look at all of these quantum numbers, here are the possibilities for 4F. N, L, M sub L. I'm going to make a little table here. So if N is 4, L, and here I should say L is equal to, I got lazy here. L could be equal to 0. L could be equal to 1. Oh, I'm sorry. They said F, so it's got to be a 3. My bad. Okay, so here L is equal to 3, but M sub L could be negative 3. I like to start with the smallest number. If N is equal to 4 and L is equal to 3, M sub L could be minus 2. 4, 3, minus 1, 4, 3, 0, 4, 3, plus 1, 4, 3, plus 2, and 4, 3, plus 3. So these are all the possible combinations for N, L, and M sub L. Now let's go into a little more detail here about this N, L, and M sub L. So N is equal to the shell. L is called the subshell. We talked about that a little bit earlier. And remember, we have 4 subshells. We've got the S subshell, the P subshell, the D subshell, and the F subshell. And M sub L is equal to the orbital. Now, the orbital type depends on the subshell type. It turns out that your orbital types are also S, P, D, and F. Okay, so let's take a look at what these numbers mean when we talk about shell, subshell, and orbital. So here, the shell is the 4th shell. This is a 3, which makes it an F subshell, and it also makes it an F orbital. This is a 4F subshell and a 4F orbital, so these are all 4Fs, as it turns out. But they're not identical 4Fs. There's 7 different 4Fs. All right. Now, it's going to take you a while for you to figure out how to work these numbers. Don't let that daunt you. Just keep working away at it. Okay. Let's take a look at another one here. Okay, so we've done this one. A possible excited state of the hydrogen atom has the electron in the 4p orbital. So 4p means that n is equal to 4. And remember, for the p, I'm going to make the list once again. If L is 0, 1, 2, or 3, the letter designation, or the subshell, is S, P, D, F. How do you remember to start at 0 instead of 1? I don't know, but you just better remember that. How do you know that 0 correlates with an S, 1 with a P, 2 with a D, and 3 with an F? I don't know. You need to figure out a way to remember this order. Some people do fine with it, some people don't. Hopefully you do fine. Okay, so here, if we have a P, I see that that's a L is equal to 1. Okay, a possible excited state of the hydrogen atom has an electron in a 4p orbital. List all possible sets of quantum numbers for this electron. Now, we're looking at 3 quantum numbers here. It turns out there's a 4th. We haven't been introduced to that yet. But the possible quantum numbers are as follows. If you got a 4 and you got a 1, M sub L can be -1, M sub L can be 0, and M sub L can be +1. So those are the 3 possible sets of quantum numbers for a 4p subshell. Okay. All right. And then we have how many subshells occur in the electron shell with the principal quantum number 4. Okay, so when they say subshells, they're talking about how many L's. So if n is equal to 4, I'm going to make my little list here. If n is equal to 4, what is L equal to? Can L be 0? You bet. Can L be 1? You bet. Can L be 2? You bet. Can L be 3? You bet. Can L be 4? No, because L has to be 1 less than n at the maximum. Now, this says how many subshells. Well, if we look at the subshell type, I used to call this the letter, right? This is a, let's see, how do we remember the letters here? Some people do fine, some people do fine. So how many subshells occur in the electron shell with the principal quantum number of 4? Turns out you have 4 subshells. And actually that works pretty good for any principal quantum number up to and including 4. If n is equal to 1, you have 1 subshell. If n is equal to 2, you have 2 subshells. If n is equal to 3, you have 3 subshells. If n is equal to 4, you have 4 subshells. But then it gets tricky after that. If n is equal to 5, turns out you only have 3 subshells. And if n is equal to 6, let me think about 6. 6, we only have 2 subshells. And if n is equal to 7, right now we have 2 subshells. But for the first 4 shells, you can see it's as easy as 1, 2, 3, 4. Okay. All right. Let's put that off to the side. And some more working with these numbers. Explain briefly why each of the following is not a possible set of quantum numbers for an electron in an atom. So let's explain why A is not possible. And here we could say if n is equal to 2, L can be 0 or 1. Why? Because L is equal to 0 all the way up to n minus 1, and 2 minus 1 is 1, so you can't have L equal to 2. So that's A. How about for n equal 3, L equals 0, and m sub L equal negative 2? Well, if n equals 3, L can be 0, 1, or 2. So that works. But if L is equal to 0, m sub L has to be equal to 0. And m sub L in general is equal to 0 all the way up to plus or minus L. Well, if L is 0, we're talking about m sub L can be 0 all the way to 0, which means it can only be 0. Okay, C. N is equal to 6, L is equal to 0. Well, that's possible because if n is equal to 6, L can be 0, 1, 2, 3, 4, or technically 5. Okay. Now, again, here we have L is equal to 0 and m sub L equal 1. Well, if L is equal to 0, this is the same as B. If L is equal to 0, m sub L has to be 0. Okay. What is the maximum number of orbitals that can be identified by each of the following sets of quantum numbers? If none, explain. Okay, so let's take a look at each of these. What is the maximum number of orbitals that can be identified by each? So here for A, we've got n equal 3, L equals 0, and m sub L is equal to plus 1. So can L be 0 if you have a 3? Yeah, it can be 0, 1, or 2. Can m sub L be plus 1 if this is a 0? And the answer is no. So this is none, because if L is equal to 0, m sub L has to equal 0. Okay, how about letter B? Maximum number of orbitals. Well, for n equal 5 and L is equal to 1, m sub L has to be equal to 0 or plus or minus 1. So that means we could have a 5, 1, negative 1, a 5, 1, 0, or a 5, 1, positive 1. So here, when I say m can be 0 or plus or minus 1, that means given n and L stay the same. So that's why I have this written out this way: 5, 1, negative 1, 5, 1, 0, and 5, 1, positive 1. So here we're looking at 3 orbitals. Okay. How about C? For C, we're looking at n is equal to 7 and L is equal to 5. So what are the possibilities for m sub L? Well, M sub L can be 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, but it can't be plus or minus 5. So when we look at all of the quantum numbers, you could have a 7, 5, negative 4, a 7, 5, negative 3, a 7, 5, negative 2, a 7, 5, negative 1, and then I'm going to write 7, 5, 0 here, and then I'm going to do a 7, 5, plus 4, a 7, 5, plus 3, a 7, 5, plus 2, and a 7, 5, plus 1. So how many orbitals is that total? 9. So that's letter C. What about letter D? Okay, so letter D says n equal 4, L equal 2, and M sub L equal minus 2. D is none. Oh, I'm sorry. My bad. So here we can have 4, 2, negative 2, and that's 1 orbital. Because if n is equal to 4, L can certainly be 2. It can be 3. It can be 0. It can be 1. Now, if L is equal to 2, what are the possibilities for M sub L? Well, M sub L could be anywhere from 0 to plus or minus 1 to plus or minus 2, and there's the minus 2. So this represents precisely 1 orbital. Okay, so let's take a look at another 3 problems. State which of the following orbitals cannot exist according to quantum theory. Briefly explain. So when we have a 2s, the quantum numbers are 2 and 0. So I'm going to make that chart once more. If L is equal to 0, 1, 2, 3, the subshell is S, P, D, F. So when we talk about a 2s, we're talking about a 2, 0. And this is, of course, N and L. So I'm going to make a little list here, N and L. So for a 2s, you got 2 and 0. So is 0 okay if you have n equal to 2? Absolutely. How about a 2d? So we're talking about a 2 and a d is a 2 right there. So is it okay for L to equal n? And the answer is no. L cannot equal n. L can be as much as 1 less than n, but it cannot equal n. So how about a 3p? So we're talking about a 3, 1. Can L be less than n? Absolutely. What about a 3f? Well, we're talking about a 3, 3. Can L equal n numerically? Nope. So here's the briefly explained part. What about a 4f? So 4 and f is 3. Can L be 1 less than n? Absolutely. How about a 5s? So 5, 0. Can L be 0 when n is 5? Absolutely. So there's only 2 here that don't work, and they don't work because L cannot equal n, but also L cannot be greater than n. Okay, L has to be less than n. Okay. Write a complete set of quantum numbers that quantum theory allows for each of the following orbitals. So for A, 2p, we're talking about n and L being a 2, and the p is going to be a 1. So I'm not rewriting the list. I'm doing this from memory now. You might want to look at your list. So what can M sub L be? It can be minus 1. We can have 2, 1, 0, and we can have 2, 1, positive 1. So that's a complete set of quantum numbers that allows for each of the following. Now, how about B, where we're talking about a 3D? So 3 is the shell, D is the subshell, and remember, some people do find 0, 1, 2, so D is a 2, and M sub L can be -2, or it can be -1, or it can be 0, or it can be +1, or it can be +2. So those are the sets of quantum numbers that work for a 3D. How about a 4F? What are the possibilities? Well, for 4F, N, L, and M sub L, N is 4, and because it's F, it's 3. Some people do find, right? 0, 1, 2, 3. So 3 is F. You got to remember that the first L is 0, not 1. Okay, so M sub L can be -3, 4, 3, -2, 4, 3, -1, 4, 3, 0, 4, 3, +1, 4, 3, +2, 4, 3, +3, and that's it. So those are your possibilities. Okay, lastly, a particular orbital has n equal 4 and L equal to 2. What must this orbital be? Well, since n is equal to 4 and L is equal to 2, remember for L, 0, 1, 2, 3, the subshell is SPDF. So when we talk about a 4-2, we're talking about a 4D. So the answer is letter D. All right, so we've had quite a bit of practice with those quantum numbers and trying to figure out what is an acceptable set. It's something you're just going to have to practice with. It's not intuitive at all. It takes practice. All right, we'll see you later.